a history talk, and the organizers were actually struggling who we should ask. And it was Ron Stern's idea, why not the obvious one? And amazingly, Rob agreed to do this. So I'm very happy that you're going to listen to this unique lecture on the history of low-dimensional topology.
Well, I'm so wired here that either I'm going to explode or else I have to say something very profound. So I think what I had in mind when I was asked for a history talk was I was thinking of triangulations and Hauptvermutung. But then I was reminded also that this is a low-dimensional topology talk conference, and therefore the calculus was more suitable. So that's why I'm going to talk about that. Now, this is going to be a historical talk, and so it's really how it is I happen to get into the calculus. And so along the way, I think it'll have some interesting points that are interesting to students, perhaps to somebody else. There's some people here I think who know every word I'm going to say, but I'm not going to look at them, and you're not here. So actually, just a bit of preamble, because Ron Stern mentioned this when he was talking about coming from high-dimensional topology and getting into four manifolds. And the same thing happened with me, which is partly connected with triangulations, that when Larry Sieberman and I finished our work, we realized that the Z2 obstruction to triangulations, or to uniqueness of triangulations, the Z2 obstruction really came from Rocklin's theorem, which is a four-dimensional theorem. And you know, all this higher dimensional stuff boiled down, you could just sort of take a high dimensional manifold, you kept slicing it with sub-manifolds, and finally you got down, you actually didn't get to dimension 4, but you got to really dimension 4 across a circle or something. And you found a signature, and then the signature, you wanted something to signature 8, and you could only get something to signature 16 that was spin in dimension 4. That's Rocklin's theorem. So things just sort of naturally led to questions in dimension 4. And the other phenomenon that was happening in those days was that there was a lot of success in surgery theory in high dimensions, and the simply connected case was in pretty good shape, and the non-simply connected case was boiling down to hard questions in algebraic L theory, and is really turning into more of an algebra topic. And so what we geometrically minded older people supposed to do? Well, we turned our attentions to dimensions 4, 3, that sort of thing. So that's sort of a preamble as to why I was thinking about these things. And then the specific thing that happened, so this is, you know, one of these serendipitous type stories. I was at a conference in Tokyo in spring of '73, and I must have been standing next to Takao Matsumoto, who was talking to somebody, and he kept mentioning the Kummer surface. And I don't know, somehow it stuck in my mind. So I came back to Berkeley with that in my mind. And coincidentally, let's see, I had gotten to Berkeley in January '72 and met Arnold Cass, who was actually an assistant professor here, and discovered that he liked to run, so we used to run. And in particular, we used to run from the gym up to, this wasn't here, but to the end of the fire trail and back down. That was a good hard run, as some of you know by now. And so I knew Cass, and Cass was a recent PhD student of Kodaira. And so he knew all sorts of stuff about complex surfaces, of which the Kummer surface was one. And so I asked him. He was also rather geometrically minded as opposed to being an algebraic geometer. So he was just the right person. And incidentally, we used to call it the Kummer surface in those days. I'm not sure why, because the Kummer surface is actually a specific complex structure on the K3 surface. K3 surface now refers to the smooth, underlined smooth four manifold, which has many complex structures. And the Kummer surface is just one of them. But if you look at our writings back in the 70s, somehow we called it the Kummer surface instead of the K3. Although Cass told me, so we knew that K3 was Kodaira, Kähler, and Kummer. No. No?
K2.
K2?
Yeah.
The mountain?
Yeah.
Oh, well, okay, so it was also maybe a play on the mountain K2, but K3 was, those three names were those three people. Anyway, so we started to talk, and that's how I really got into four manifolds, and also how it led to this calculus of framed links. So I really want to start by sort of telling you some of the things that Cass told me about complex surfaces, and you'll begin to see how this led into the calculus. So that's going to form the first part of this. Yeah. So I don't quite remember the exact order in which he told me things or which questions I was asking, but certainly he said that the K3 surface, the Comet surface, as we called it, K3 surface was an elliptic surface, which meant that there was a map to CP1, the two-sphere, some projection P, and the non-singular fibers were tori, the two torus. And then there was a batch of singular fibers which had been classified by Kodaira, beautiful work in the early 60s. And so he told me there was fibers, well, there was the torus, but then there was the fishtail, and there was the cusp, and then there was more interesting ones, and in particular there was one that was the cusp, and then there was one which we called E9 because it's E8 with one more in the long tail. So that was drawn there should be 9 of those. You know what E8 usually looks like with 5, 3, and 2, but this is a 6, 3, and 2. This is the curve in the middle. You know, it's also the diagram. And then there's 6 of these. So it's a dual of that graph. So there's these fibers and some others. And so I was asking him, you know, what are these fibers like, and so on. Well, the fishtail, this is a two-sphere with a double point. That's the double point right there, and this is the way the algebraic geometers drew it. And this is a cusp, so that meant if you looked at this 4-ball, then out here, the curve intersected the 4-ball and the trefoil knot. So that's what this knot is. And then this is just the cone on it topologically. So this again was a two-sphere, and it had this singularity. It was smoothly embedded, except it had singularity. And then all of these, in the E9, all of these lines are two spheres, every one of them, and they all have self-intersection -2. So they all have normal bundles, and they're all self-intersection -2. So that was known, and Cass, let me write his name, Arnold Cass. He left math around 1980 and worked as an engineer for Boeing for about 20 years on helicopters and such things, and then he retired and took up microbiology, and he used to volunteer at the University of Washington microbiology group or something doing lab work, and they finally decided they better start paying him because otherwise he might go do free work for somebody else. So he's been actually working on DNA, and he had an interesting career. He's an interesting guy, and it's too bad we lost him in mathematics. So anyway, so there's these fibers. So then the question, well, as a topologist, I knew handle-body theory. So what do these things look like? Well, so right off the torus, we used to draw the torus by the picture many of you know. So here's a pair of one handles. This is a 4-ball. Underlined here is a 0 handle, which is the 4-ball. And then you add a 1 handle to these 2 feet. And you add another 1 handle to those 2 feet. And so there's the 4-ball with a pair of 1 handles. And then you add a 2 handle, which goes over, 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 and then back to where you started with, and it has framing 0, and that should be a picture of the torus, which you all know. And then because this is 4-dimensional, it's a torus cross B2. So that was a picture then of a neighborhood of this torus, and there's nothing very interesting there because it's a non-singular fiber. But then for the fishtail, well, so the fishtail was drawn with the same picture. And then one vanishing cycle. So that could be drawn this way. Now, it took a little while to understand this. I mean, several things were going on when I was trying to learn this. One of the things was, well, so this handle body picture came after a little bit more thought. But the point is, if you cancel this one handle with this two handle. So this is a two handle, which is a two cell attached, a thickened two cell attached by running along this arc and back over the one handle to where you started. So you attach, this is like attaching, if you think of the torus here, here's a meridian, and you attach a two handle across it. Well, then when you cancel this, well, I'll never get anywhere if I say much about canceling, so I hope you know what that means. But when you cancel this, you then end up with this one handle is still there. This one has been gone, and this two handle does this. And the crossing here, looks like that. So this is still 0. And so now you see, you sort of should see the two-sphere with a double point. Because if you take a, you can go from the double point inside the two-sphere around back to itself. That loop is this one handle. And then you cap off, and in some sense, if you pull this through itself, you get a point of intersection, and then it slides off to a regular disk. So there's built-in point of intersection there. So that was the picture of the fishtail fiber. And one thing you learn is that, this is a vanishing cycle. So this is a circle which, as you move in the base two-sphere, so Denis, in his talk, was drawing these pictures. So here's a two-sphere, and we have a non-singular fiber with a circle around it. So this is just an ordinary torus. And then you're going to have a singular fiber. This is the cusp, the fishtail. And when this disk expands, you just got a bigger and bigger torus cross disk. But then suddenly you pop past that singular fiber, and what happens there is a vanishing cycle has been added. And so that's when this guy appears. So in the base, as it expands, you see a circle, and that circle is pinching. Well, when the circle pinches, that's a disk. And that's the disk, or the two handle. When it's thickened, it's been attached. And, well, it's got a -1 framing. Now, I think the nice picture here, for those who have never really seen this or thought about it before, the nice picture as often occurs, you can see by doing the real case and cutting everything in half. So in the real case, instead of having a torus fiber, you'd have a one-dimensional fiber. And in this case, locally, it's going to consist of two arcs. And down the base now is one-dimensional. Could be the circle, but this is just a local picture. So here's the base, and this is what you have over this point. And now that point is going to expand. So if you take an interval here, you actually have you see these arcs moving to the right as you move across this interval. And this corresponds to, well, here you have a disk which is expanding, there you have an interval which is expanding. And now, what can happen, what kind of a singularity could you have here that this is going to go past? So this is going to be some kind of a singularity. And so what would happen is that you're going to add a one handle, not a two handle as in that case, but a one handle, and it's going to be a one handle with a half twist in it. So as you pass the singularity, you're going to add this one handle with a half twist. And when you finish, you have then got, this is now continuing, and it goes down like that, and this side goes over like that. And you've put this half twist in there. So that's easy to see. So that's the real analog of these vanishing cycles. Here, the vanishing cycle is a 0 sphere instead of a 1 sphere. You're adding an arc. You're adding a one cell, but then you thicken it, and it's thickened with a half twist in it. So it's not the trivial one handle, but instead it's got this half twist in it. Well, the analog in complex dimensions then should be you double, so you add a 2 cell. It's got to have a twist in it, so it's not attached with framing 0. It's going to be attached with framing, well, why not -1? The complex structure says -1 instead of +1. So that's a way to understand what this vanishing cycle is. So that came from Cass, and then it turns out that you get the trefoil knot. So this was the fishtail. You get the cone, the cusp, by adding a pair of vanishing cycles. So one here and then one here. And it's an easy exercise to cancel both one handles, whereupon all you have left is this 2 handle that had framing 0. And when you do that, this 2 handle turns into a trefoil knot, as many of you would have seen before. So this becomes the trefoil knot. Right-handed one because they're -1s. So, so Cass, the algebraic geometry did not draw handle bodies like this. So part of it was, for me, was to translate algebraic geometry into handle bodies. Second, another thing that he said was that if you perturb any of these other non-singular fibers, they break up into fishtails. So everything is done with all the singular fibers are obtained by some number of vanishing cycles attached to the torus. Well, okay, so that was interesting. The K3 surface, put this here for a moment, the K3 surface, the whole thing had, if you like, 24 fishtails over CP1. And the point was that if you started with a torus, I should also say that something else they knew was that when you went past a vanishing cycle, there was a change in the monodromy. So beforehand, this was a trivial torus bundle over the circle. After you went past this, you put in a right-handed Dane twist along the vanishing cycle. So here you're putting in a whole bunch of 24 right-handed Dane twists. But the vanishing cycles alternate between, so if I were to draw the whole K3 surface, I'm not supposed to write over there. If you draw the whole K3 surface, you just have 24 of these. And what you're doing is attaching these vanishing cycles alternately. So you got a picture that goes like this, this one, and then this one, etc. So they weave like this. And then if you calculate the monodromy here, you'll find that after you go through 24 of them, the monodromy is trivial. So at this point, you then have a trivial torus bundle over the last circle, and you fill it in, and you've got a closed manifold. So all these things were known to the algebraic geometers. But one thing that was in 1973, calculating or seeing a basis for the homology of the K3 surface was not very well understood. Spanier had written a paper in which he actually calculated the cohomology of the K3 surface. But what the generators were in terms of these pictures was not so clear. In particular, well, I won't go into that. It was just not so clear, and that was something that was clarified. Okay, then there's also blowing up and down. So blowing up and down, I won't say much about. I mean, you know that the algebraic geometers would draw a curve with framing, with self-intersection n, and then they'd blow up a point, and this would go to n minus 1, I hope. So they would do things like this. They'd take curves that intersect, n and m, and they blow up this point, and then they no longer intersected. So they would draw pictures like this. This was their schematic notation. So then the question is, what did that mean topologically? Well, first place, you could just blow up a curve. And if you blow up a curve, that means you take your manifold and you connect some with CP2 bar. And I think I'll assume you all know that. And I won't say more. I mean, well, let me just say this. When you blow up a point, you have all these complex lines going through it. So there's CP1, you're in C2 locally. A point has CP1 worth of complex lines. And what you're doing is you're taking out that point and you compactify each complex line separately. So each one of those lines needs to get a new point. Well, there was CP1 worth of these lines, so you're going to add a CP1, 1 point for each complex line. So that's that curve. That's the CP1 that you added. This is a two-sphere, CP1. And, well, again, let me just say this. Think about the real case where you take the plane and you compactify each real line and you connect some with the real projective plane. You put in a Mobius band into that. So I'll stop with that. But that was not so hard to understand. But then, what was the difference between blowing up? I could start with that line, and I could also start with this line, and I could blow up this point instead of this point. If I blew up that point, it would look like this. And what was the difference between those? What difference does it make whether the point you blow up is here or in here? Well, it turned out that the difference was that you take this two-sphere, this two-handle, and you slide it over this minus 1. And so that was the beginnings of handle slides, at least in this context, that you slid this over the minus 1, and then you got this picture. So here, you slide this two-handle with framing n over this one. Well, this one, the n1's over this two-handle, which is minus 1. And when you do that, you get that picture. Because in particular, the way to draw this was to think of this as the zero handle, and then you had attached a handle with framing n minus 1 to this circle, and another handle with framing minus 1 to a linking circle, because this circle linked that circle. So this was the picture, the handle body picture for this picture in algebraic geometry. And whereas down here, this picture was this and this. And so if you slide this, because here your four ball is, your zero handle is that, and there's a handle attached to a circle which is disjoint from that circle. And so then you slide this over this and you get that picture. So this choice of where you blew up points in the algebraic geometry, you translated that into handle slides. So there were the handle slides. So now, handle slides don't change the four manifold. Blowing up changes it by connect summing with CP2 bar. And so at some point, one begins to wonder, well, what else do the algebraic geometers do? Well, they would make the following comment. So here's an argument that Arnold Cass would make. It wasn't his, but he knew it. It would show that E1, or what we call the half-Krummer surface, but E1, so remember there's the E2 is the K3 surface. E1 means well, E1 we know is CP2 with 9 points blown up. So it's the rational elliptic surface. So Well, why was this true? I mean, I've defined it that way, but I mean, E1 is really an elliptic surface with 12 fishtails. So how did the algebraic geometers know that these were the same? This is a classical old fact for them. Well, they wrote E1 as the torus, two torus cross the two sphere, and you divide out by an involution, sigma, where sigma, so sigma on the torus, you just rotate 180 degrees, and sigma on, same thing on the sigma on the two sphere, you again rotate 180 degrees. So there's those two, so then you divide out here. Now, I now want the projection for my purposes to the torus. And what do you see here? Well, you should see 8 singular points. These are the 4 points here crossed with the 2 fixed points here. So there's 8 singular points in which are fixed points, 8 fixed points. So under this projection, when you divide the torus by sigma, you get the two sphere. So here's P1, CP1. And over it, you've got all these fibers, which are two spheres, except that you've got 4 fibers which have a pair of fixed points on them. So this is non-singular, but here these are singular points. This is not a manifold. So what you have here is RP3. Because on the 3 sphere linking these points, there's an involution and you get RP3. So you cut these things out. To make a manifold, you cut these out and you glue in, so the way they drew it was you glue in a 2 sphere, the cotangent disk bundle, turns out. So you glue in a 2 sphere with a -2 framed normal bundle. So if you take the 2 sphere and the disk bundle with self-intersection -2, the boundary is the RP3. And that turns out to have the right orientation for this picture, so it's a cotangent disk bundle. So you do that in each place. These are all CP1s with self-intersection -2. And now you have a manifold. And this manifold is a description of E1, which they knew. You can also get the K3 surface by taking the torus across the torus. You have 16 of these, do the same thing, and that's one complex structure on the K3 surface. But here we're just doing this one. Now, question is, this is still a 2 sphere, but what's the self-intersection? So if I call this X for that fiber, then X dot X equals what? Well, again, the algebraic geometers knew how to calculate that because this singular fiber could be pushed off itself and therefore had self-intersection 0. So you could just take the self-intersection of this, which was X plus A plus B, if this is A and B. And if you take the self-intersection and calculate, you get this X is with multiplicity 2 because this 2 sphere is hit twice because this is a fixed point. And so the 2 sphere maps onto itself by double covering. So that's a 2, but not the other. So when you do this, you get 4x squared plus 4xa plus 4xb plus a squared plus b squared. There's no intersection of a and b. And so this is the unknown. 4 times is just 8. Yes, -2 minus 2. And so x has to be -1. So you can always work these things out that way. No, the point of this is that, so here's a picture. Why is this the same as CP2 connects some 9 CP2 bars. So this is their definition of E1. And why is it this simple rational surface? So what was the method? Well, the method was that you take these 4 minus 1s and blow them down. When you blow them down, that's 4 of these. So you split off 4 of those. And after you blow them down, you have the minus 2s become minus 1s by whatever we've done over there. So when you finish blowing down, you have this picture. And these are all minus 1s. So all I've done here is the reverse of this process. Blew down a minus 1. That changed the framing. It went up by 1. And if there's, as in this picture I erased, I guess, if there's another one, then it would have intersected there. So A and B now intersect, and their framings have gone up 1. Now, now I want to just observe there's a section across here. So I'm going to blow down this minus 1 and these 3 minus 1s. So that's another 8 minus 1s that disappeared. And when I blow down those, this minus 1 goes up to 0. There's this section. And all the others become zeros. So those are just ordinary fibers now. This is a bundle. And this bundle, turns out this section has self-intersection, I think, minus 1, plus or minus 1. And so this is S2, twisted S2, which is CP2 connects some CP2 bar. So I blew down 4, I blew down another 4, and then here's the remaining one and the CP2. So this is how the algebraic geometers would prove that those two complex surfaces were the same. Well, there was, let's see, there was, anyway, at this about, I guess it was about this point that, you know, a topologist could observe that all we were using in the complex world was minus 1s blowing down in one sense. But topologically, you could just as well blow plus 1s up and down. In other words, you didn't have to preserve the orientation as you do in the complex world. So there was this move whereby you, see, Anna, in the last lecture, observed that the 2 K moves, one of them was sliding handles, and the other one was blowing up or down. And so in particular, that meant that you could take your link L and pass back and forth between L union an unknot with plus or minus 1 framing. That's what, in handles, what would be blowing up and down. So, so at some point, you know, it naturally occurred to me to begin to wonder whether you could do this. Well, so this is being done with closed manifolds. Both of these operations, if you had a 3 manifold that bounded a 4 manifold, then sliding handles didn't change the 4 manifold. Blowing up or down changed the 4 manifold, but not the boundary. So the question then was, if given M3 is equal to the boundary of x1 and also the boundary of x2, how were x1 and x2 related? So this is sort of a relative version where there's a boundary of this kind of thing. You know, here were 2 closed 4 manifolds up there, and you could show they were related by these moves as the algebraic geometers did. So first place, you could assume, well, we'll assume x1 and x2 have 1 zero handle and only 2 handles. So that means then that this three manifold was obtained by surgery on two different frame lengths. So that's another way to state it in terms of frame lengths. Each of these is described, each four manifold is described just with let's say, a zero handle, and then the two handles are attached to frame lengths. So it's just, they're described by frame lengths. So now you have M as surgery on two frame lengths. Well, as Anna said, it had been known certainly by Licorice, who proved that every three manifold could be obtained by surgery on a frame length. Maybe Wallace was doing this at the same time, and certainly the Bordism theory people, they should have known that this was true too, because Bordism groups were being classified by Tom, but I'm not sure that this one had been worked out. So this is usually attributed to Licorice, who certainly did a nice job of it. And just to remind you, how did Licorice prove that every three manifold could be obtained by surgery on a frame length? Well, we know about Hagar decomposition, so you knew that if you took every three manifold had a Hagar decomposition, and there was this diffeomorphism of the Hagar surface by which you glued them together. So he proved, his first step was to prove that any diffeomorphism up to isotopy was generated by Dane Twists. So he was the first to do that. So now on this surface, you had a whole bunch of Dane Twists, and you did them in order, and that gave you the diffeomorphism. And the next observation of his was that doing a Dane twist on such a circle in the surface was the same as doing a surgery, if it's a right-handed or left-handed, surgery with plus or minus one coefficients on that same circle. Now the circles lie on the surface, but they're done in order. So you would take a circle, take the first circle on the surface and do the surgery. The next circle might have intersected that, so you push it in and do surgery. And then you push the next one further in and you do surgery. So the order of the Dane twists tells you how to push the circles in off of the Hagar surface, push them in and do surgeries. And so there was the frame length picture that Licorice gave us. So that meant that the three manifold, that was an existence there. The three manifold was surgery on a frame length. And then you wanted a uniqueness question. Well, how unique was it? And so this was, I don't know that it had ever been asked. I don't, nowadays, if we hear an existence theorem, we immediately say, well, what's the uniqueness version? But I don't recall that this was asked, but it occurred to me, and so we started trying to prove it, and that's a different story. This is really the story of how, well, so far, this is the story of how complex algebraic surfaces and what they knew. If you then understood it and thought about it in terms of handle-body theory, this is what you were led to. Struck me ever since that these special cases, well, the complex surfaces, or where you have nice geometries or something like that, you understand those well, and then you see how to get topology out of them by generalizing them and seeing what you can get, and that we actually keep coming back. We keep coming back to the beautiful, simple cases, coming back to Seifert fibered three manifolds, for example, and getting more out of them. They're never done. When I was a student, surfaces were classified. I thought that was the end of the subject, and surfaces weren't interesting. Well, there's the diffeomorphisms. We also in those days thought that the whole point about bundles was to show that was our characteristic classes, which showed that they were distinct. Use those invariants to show that bundles were different. And then at some point, gauge theory came along, and we realized that it's actually the trivial bundles which were the most interesting because of the different trivializations. So, we keep coming back and discovering more from the beautiful examples. So now, since we're doing history a little bit more, so I can say something about the proof in the last few minutes, how it went, because it diverged rather. The proof didn't have anything to do with this algebraic geometry. The algebraic geometry suggested that these two moves were all there was. At least it hinted at that. But the proof is quite different. So the whole story about that. I was in Warwick in the summer of '74. That's when this was nearly done. And I talked to Colin Rourke about it, and I didn't realize it at the time when I came back to Berkeley that he was continuing to work on it. And it was only a while later, and so we both were working. He was trying to do it using PL handle body theory, and I was doing it, as I'll say in a minute, involving surf theory and families of Morse functions. So I was doing the smooth version, he was doing the PL version. And he got stuck on trying to deal with three handles in the PL case and was just stuck. And so I got stuck on three handles in the smooth version, but I didn't know it. So I wrote up the proof and sent it in, submitted it, and the referee came back. I think it was Alan Hatcher, but I don't know that for sure. Anyway, he was a good referee, and he found this mistake, and I worried about it for 2 weeks before I figured out how to do it. And so then the paper appeared. And later on, I found out from Colin that he'd been smart enough to realize that he had a three-handle problem and didn't write it up and didn't submit it, whereas I missed it. The referee found it, and well, then I did find the way around it. So Colin had also been talking to Roger Finn, and so Finn and Rourke then, as you know, they had a paper in which they showed these two moves were equivalent to what they called a K move, which is actually the one that's, so it goes like this. You can have a whole bunch of things passing through one of these, and these have different framings. They may be the same, some of them may be the same component, but not all. And anyway, this goes back and forth between, so now you just put in a big minus over plus one, full twist. There's just a full twist in the same curves. So you can go back and forth. So you're basically blowing this down and getting that. And there's really just this one move. And actually, this is the move I believe that Reshetikhin and Traev used when they were checking that with their universal, their quantum algebras, et cetera, that their algebra was working out right. And this is the move that they checked it on. So this was first observed by Finn and Rourke. Now, so I'll make just one remark about that. Later, so here's a remark. So I proved this uniqueness theorem, that those two moves were enough. And there was no applications of this. This was proved in '74, published in '78. There's no applications until 1989 when Reshetikhin and Traev used it to show that they had an invariant. There's no applications before that. But there was a moral application which said that, well, so you had two three manifolds given by two framed lengths, and you wondered if the three manifolds were the same. So morally, this theorem told you, well, if they're the same, you can get from one length to the other with these moves. And so that sort of gave people faith that this was a way to try to show things were the same. And then the same thing with closed four manifolds. This was really a four manifold theorem. And it was used, so then the people whose names I really ought to mention are the ones who took this and really made a subject out of it. Most notably, I think, is Selman Akbulut, who has written many lovely papers using this calculus. In particular, I think the one maybe I like the most is that he still has the smallest exotic four manifold. The problem is that it has a boundary, but he has he showed that there exists a contractible smooth four manifold which has two exotic structures in the following sense. You fix the smooth structure on the three manifold, and they have unique smooth structure. So you fix that, and then what there's an involution, which is a homeomorphism. That's a diffeomorphism on the boundary. And so then you take this homeomorphism and pull the standard differentiable structure, you carry it by the homeomorphism to a new differentiable structure, which is the same on the boundary, because the boundary only has one. And so those are two different smooth structures on this contractible manifold REL boundary. So it's a relative theorem, but nonetheless, that's, And that was done by a humongous bit of work involving the K3 surface and all kinds of handle slides and pictures for that. And he's, so then another comment about four manifolds is that throughout the 70s, Selman and Bob Gompf, Paul Melvin, there may be the three. John Hare did it in the 70s, and then he dropped the subject. So, but I could include him too, and some others did less. But I think those who kept going and did the most work with this were Akbulut, Gompf, and Paul. But one of the things was to understand four manifolds, and we immediately saw four manifolds that looked different, and we couldn't prove they were different. And we tried to find invariants using this kind of stuff, and there was no hope. Didn't work. And it was hard to show things were the same because we thought they were different. Well, then along came gauge theory, and of course the story is that all sorts of those things were actually different, and we couldn't prove they were the same. But we still have no real tools for showing two smooth four manifolds are the same if we think they're the same. Then how do you prove it? Well, so Selman does this with the Charlemagne manifold, with some others. He's shown that these things are standard by this method, but it's awfully hard work. And Gompf did this with this with this double cover of a exotic RP4. He showed that was S4 by a beautiful trick. And so, and there's actually progress of this these days. I mean, you heard about broken Lefschetz vibrations, but again, Selman and some of his collaborators are working with positrons and quarks and plugs and doing interesting things with that. So there's interesting stuff going on. Now, maybe maybe the nicest thing I can do for you is actually stop early instead of stopping late. Especially Mike Friedman. He just disappeared. Yes, he needs to get going, but I want him on the history panel for a while. So let me stop here and we'll get history started earlier.